Okay. So we continue full force in the month of July with seminars, just to ensure that you go to the beach after 2 p.m. at least. So it is a great pleasure to have with us Minas Karamanis. And Minas came to us all the way from Berkeley just to give the seminar. Actually, this is not quite true.
Actually, that's not true. I was in Germany. So it was.
He was in Germany and then he decided to come to Crete. We are really glad he can join us for a few days. And Minas, he obviously, as you know, as you can tell by his last name, he comes from Greece. He graduated from a high school in northern Greece, the picturesque city of Drama, who is the second most interesting city in northern Greece after Ceres, and the locals actually know what I'm talking about. So then he moved to the University of Thessaloniki, where he got his undergraduate degree. And then he decided to continue and go abroad. So he went to, instead of choosing the colonies, he went to the UK, in particular to Cambridge, where he did a master's there. The well-known tripos, the master's in theoretical and applied physics. And he realized that probably string theory was not the best thing one to do, actually. So he moved, he decided to do astrophysics and cosmology, and he got his PhD from Edinburgh. And then he moved to the colonies. He went for his postdoc at Berkeley, where he is there, and he's going to talk to us about his recent work. Minas will be with us today and tomorrow, so we'll have lots of chance to interact with him.
Thank you, Vasilis, and thank you very much for the invitation. It's a great honor to be here. So today, my plan is to talk about statistics, machine learning, astronomy, and most importantly, computation. I will assume no previous knowledge of any of the aforementioned topics. Many of the things that I will present, you've probably seen this before, but hopefully by the end of this talk, you'll see this from a different perspective. Okay, let's start with a bit of background. There are two types of problems that we try to solve. There are the so-called forward problems or direct problems. These are problems where we have various factors and we want to predict what sort of effects these factors have. For example, we may have a hypothesis or a model or a theory, and we want to know what kind of universe we expect to see out there based on these assumptions, based on this theory hypothesis. And there is the opposite type of problems, so-called inverse problems. These describe problems where we have some observations, measurements, data, and so on. And we want to infer what was the underlying cause of these effects. So given a list of hypotheses, we want to find out which was the correct one. The reason we care about these two types of problems is because they are very important in what we call the scientific method. So if you remember from your high school years, we have this very simplified approach, we have these two components, the data and the hypothesis, or the theory and the measurements and so on. And we want to create a loop to this to improve our knowledge. One way to go from this, from the hypothesis, starting from the hypothesis and go to the data by making predictions. Given the hypothesis, we predict, again, what the universe should look like. And we call this deductive inference because we make deductions. And the usual tool to do this is by making predictions. We have a model and we predict. And of course, there is the opposite approach to go from the data, from the measurements to the hypothesis. We call this plausible inference. And usually when we do this, we say that we do hypothesis testing, or we say that we do parameter estimation. Now, based on the previous slides, you can probably tell that deductive inference is a forward model, is a forward problem, and plausible inference is an inverse problem. Now, in this talk, we will focus mostly on the plausible inference, so the inverse problems. And the reason is that those are much more difficult to solve in general. And there are good reasons for this. The main reason that those problems are difficult to solve, so to infer which hypothesis is correct, given the data that we have, is because those problems are not mathematically well posed. So for a problem to be well posed mathematically, it needs to satisfy these three conditions: the existence, uniqueness, and stability of the solution. So there needs to be a solution to the problem. That solution needs to be unique. And furthermore, that solution needs to be stable. And by stable, we mean that if we change the data a little bit, if we add slightly a bit of noise on the data, then the solution doesn't change dramatically, but only shifts a little bit. So it turns out that plausible inference, so inferring model parameters from the data, violates the second and the third conditions from this list. So given the data, because the data are noisy and uncertain, we can never tell that there is a single model, single hypothesis that's correct, and all of the rest are wrong. And furthermore, because we have noise again, the results are also sensitive to noise. So if we cannot tell whether a hypothesis is correct and whether a hypothesis is wrong, what's the next best thing we can do? So given a list of hypotheses, if we cannot discard all of them, but a single one, we can at least rank those hypotheses, right? We can say this is the most plausible one, this is the second most plausible one, and so on. So we can assign some sort of score to this hypothesis. Well, we call this score a probability. And of course, this is not anything new. It was legendary physicist Edwin Keynes, who advocated that probability theory is nothing more than an extension of logic. And if you haven't read this great book, please do. So what we mean by that? Let's say that we have a list of hypotheses. Let's say that we have some measurements from measurements of the position and velocity of a planet, like Saturn, and we want to estimate some parameter about the planet, some characteristic, the mass of Saturn. So we can list all those hypotheses and say that first hypothesis is that the mass is between 0 and 1 in some units. The second hypothesis that's between 1 and 2, and so on. And then based on the data that we have and our understanding of the universe, this means classical mechanics in this context, we can assign different probabilities to those hypotheses, right? We can make a plot, looks like this. So here you can see, for example, that the most probable hypothesis is 8.5, but there's something else here, right? There are also other hypotheses that are also quite plausible based on this picture. So this object over here that we plotted, which we call the posterior distribution, describes all the information we have about this parameter. It describes both the best parameters, the best estimates we can get, but also, and most importantly for science, the uncertainty about those parameters. We can never say, for example, based on this plot, that the mass of Saturn is 5 10 to 8 kilograms, but we say that most probably about this. We also have some uncertainty there. Now, of course, there is no restriction to work only with discrete hypotheses. We can also work with continuous ones, and then we get something like this. And if we want to calculate the probability, we just integrate in a specific range. Now, let's focus more on this object over here, this probability of the parameter, in this case, the mass of Saturn, given the data and the model, classical mechanics in this context. I already told you that this is called the posterior probability. And this relates to some other components, some other probabilities using Bayes theorem, which you can see here. But first, let me explain what the symbols mean here. Theta is usually the parameter of the models. In this example, it's just the mass of Saturn, but of course, it can also include other parameters like the radius of Saturn or something else. D is the data, and 10 is all the other assumptions that we made. So the model, the classical mechanics, Newtonian mechanics, everything else goes there. And you can see here that this posterior distribution is actually the product of this likely to function, which is a function and not probability distribution because it depends on theta, which is the only thing that varies here. D, the data are fixed, times the prior distribution and divided by the so-called evidence, which is just a single number. Now, the prior distribution is also very important. It describes the probability distribution of the parameter, the mass of that parameter. Even the model, but you can see here that it's not conditional, the data, like the posterior. So it is our state of knowledge about that parameter, about the mass of Saturn, before actually seeing any of the data. We can simplify the notation a little bit. So we have P of theta to be the posterior, L of theta to be the likely function, and I of theta to be the prior distribution, and Z to be the evidence, which is just the normalization factor because we can just integrate the top and get the evidence. Now, what does this look like graphically? We have again Bayes theorem. Posterior is proportional to the likelihood times the prior. This is the prior. this is the likelihood, and we care about the product of this, or more appropriately, the normalized product of this. Now, this is all very nice and very simple, and you've probably seen this all before. But the problem with this picture is that all of these flows are one-dimensional. What happens when we go to 2 or more dimensions? How can we actually represent those objects in 5 dimensions? One approach is to do this analytically, to write down functions and compute everything with pen and paper. But of course, this is not possible to do. And the alternative is to represent the posterior distribution using samples. So the idea here is that we have a collection of points in parameter space with all these samples, and optionally, some weights. So these are just some factors multiplying those, signifying the significance of those samples. And that way, we can represent any distribution, in this case, the posterior distribution, the weight sum of delta functions. So we just take all those points in parameter space, we assign this weight to those points, and based on the way that those points are distributed and weighted, the mixture of this Dirac delta function is the distribution that we're looking for. Now, the next question is, okay, we have a way to, we know what we're looking for. We have a way of representing that. How can we actually get those samples and those weights? And this is the target of the so-called sampling methods, or simply samplers. So these are algorithms that are designed to produce samples from the posterior distribution. There are many flavors of this. Here, at least only 3 of them, although perhaps the most important ones, at least for astronomy. We have MCMC, or Markov chain Monte Carlo. We have sequential Monte Carlo, or simply SMC, and we have nested sampling. Astronomy is dominated by MCMC methods, and in particular specific flavor of MCMC methods, the so-called ensemble methods. I guess people used MC before. And of course, nested sampling. There are many, many codes that implement nested sampling. There are no implementations of SMC, sequential Monte Carlo, despite sequential Monte Carlo being the state of the art in other fields like statistics. Now, in this talk, I will introduce a new sampling framework. It's not a single method, it's just like a family of methods, but unifies previous approaches. More importantly, this new method we call persistent sampling unifies SMC, sequential Monte Carlo, and nested sampling. And then we will focus on a very specific member of this family, which we call PMC, or preconditioned Monte Carlo. We will show that PMC is a very efficient alternative to nested sampling. We'll show that it can produce both posterior samples and also the model evidence that Z that I showed you, because it's very useful if you want to do model comparison. And I will also show you that this can actually scale in very high dimensions. It can actually, it's parallelizable. So if you have multiple figures and you want to use all of them, you can do that. And it's more efficient. Okay, so let's start by describing what preconditioned Monte Carlo is. As I said, it's a member of the persistent sampling family of methods, but it also relies on a couple other approaches. Specifically, it relies on the so-called normalizing preconditioning, which is an approach that aims to simplify the problem of sampling. And furthermore, it relies on a very specific MCMC method, which is called preconditioned Transmichelson. Before I explain how preconditioned Monte Carlo, or PMC from now on, works, let me tell you about some of its features. As I said, it provides samples from the posterior. It can provide an unbiased estimate of the model evidence if you want to do model comparison. And furthermore, something that I haven't mentioned, that it's also very good for global optimization. So if you have a function that you want to optimize, and that function is perhaps non-convex, there's many local optima, then this is a good method to apply if you want to find the global one. And let me also tell you some of the advantages compared to other methods. First of all, it's fully, or as people say in computer science, it's embarrassingly parallel, meaning that if you have 1,000 CPUs at your disposal, the method is 1,000 times faster. This is not the case for most methods. Second, it is adaptive and it's very easily adaptive. This means that the user does not have to specify many parameters beforehand. Everything is done automatically. Everything is inferred from the actual analysis. Furthermore, and more importantly, the method is scalable. So unlike other methods that can only work for low-dimensional problems, PMC can actually scale to moderate to high dimensions. I won't say thousands of dimensions, but hundreds of dimensions, definitely. And this is very important because a feature of PMC is that it does not rely on differentiability. So you don't need to have your model written in JAX or PyTorch or Julia or something else. If you've written something in NumPy or you're using your supervisor's code which was written in Fortran, you can still use that. There's no reason to provide the gradients. Furthermore, it's able to handle multimodality. So cases where your posterior distribution is not something smooth and nice with a unique peak, something that looks like a Gaussian, but instead has multiple peaks, multiple well-separated peaks, can still sample reliably from this. Can also sample from non-linear posteriors. So if you've seen any results where posterior distributions look like banana-shaped elongated blobs, then this is not a problem for PMC. And finally, unlike MCMC methods, it has a well-defined termination or convergence criterion. So in MCMC, we usually run the code and we need to choose all sorts of ad hoc statistics to determine when to stop running. This is not the case for PMC. In PMC, there is a well-defined criteria. Once the code gets there, that's all you get. You know that you're sampling from the posterior distribution. Okay, let's start with this big family of methods, which we call persistent sampling that we introduced. What's the basic idea behind persistent sampling? The basic idea is that instead of solving a very difficult problem once, that is the problem of sampling from the posterior, you instead choose to sample to solve many easy problems. So we split the problem of sampling from the posterior into multiple easier problems. And the idea is that by solving those problems sequentially, one at a time, you get a better understanding of what you're looking for. Each problem that you solve informs you about how to solve the next one and the next one and the next one. And before you know it, you are sampling from the posterior distribution. Okay. There are many methods of splitting a problem like that into multiple ones. The one that we followed here is the so-called annealing method or temperature annealing method. The idea here is that we create a sequence of distributions instead of just one, instead of just the posterior distribution. We create a sequence of distributions like that. So you see here that we find this PT distribution. It looks like the posterior distribution, like a function of the prior and the evidence. You notice there's this factor here, the exponent here. The function is actually raised to the power of p2. And based on the value of beta, we get something else. So when beta is equal to 0, that's the prior distribution. If beta is equal to 1, we recover the posterior distribution. By allowing beta to take discrete values in this range from 0 to 1, we have a sequence of distributions, so a sequence of problems to solve, right? And if this interpolation between 0 and 1 is gradual enough or smooth enough, then it's very easy to go from the prior to the posterior and get samples from the posterior. This just shows the same thing again, but in a two-dimensional case. You can see here, for example, this box represents the prior distribution. You see those columns here, it's 3, where the posterior distribution were here. Each column represents another P0, P1, P2, and so on. Okay. What is then persistent sampling? Persistent sampling takes some particles initially drawn from the prior distribution. Those particles are just points, we just call them particles. Those are distributed according to the prior, and then using those particles, it generates a few more that are closer and closer to the posterior. So in this case, we're sampling from PT, which is some intermediate distribution in this sequence of problems that we have. And we keep doing that. We keep adding more samples, more points in regions where actually it matters. And after a few steps, we have samples from the posterior distribution. Something that you may notice here, it's important detail, is that even if the samples you'll see some samples that are extremely relevant prior or the previous distributions, but those a bit more transparent, you can see here. This will turn out to be important later on. It means that those samples have lower weights, if you think about the representation that I told you before. Okay, let me describe the method now. We start from some samples from the prior. We start from n samples. The parameter beta is a value of 0 in this case, and the temperature distribution P1 corresponds to the prior distribution. Then we generate some more samples. And at some point, at iteration t, we have generated t minus 1 times n samples. If we keep doing that, at some point, we will get to the posterior. Now, an important thing to notice here is that in order to generate samples of iteration, say, t, here is n samples, we need to take into account not only the samples from the previous iteration, but from all previous iterations. It's called persistence in this context. It means that particles do not die like in other methods like nested sampling or sequence of Monte Carlo, but instead they persist throughout the run. Okay, let me now explain how we get from here to here. There are 3 steps, 3 rules. The first one is we need to take all these t minus 1 times n samples that we have, all those particles, and assign a weight to all of these particles. Once we do this, we have now a weighted sample t minus 1 times n particles for different particles with different weights based on how well they describe that particular target distribution P sub t. The next step is to choose the best particles out of this. Here we have t minus 1 times n particles, but we want n particles for the next step. So we need a procedure, which we call resampling, to choose the n best particles out of this t minus 1 times n particles here. Now, if you notice here, if we just reweight particles from here to here, and from this one to this one, we just choose some particles, we haven't yet generated anything new. We just found a nice way of choosing the best particles from the past iterations. Now, to generate new particles, actual novel particles, we need to take those n samples that we resampled and move them around a little bit parameter space. Let me now explain how the first step in this procedure works, how reweighting works. So you probably know that if we have 2 distributions, say Q and P, and we have samples from Q, but we don't have samples from P, and we really want samples from P, one way to do so is to use importance sampling. So we compute these weights, which is just the ratio of the 2 probability distribution densities. And these are the weights for the particles, and you can use this in the sum that I showed you before in that mixture and do our analysis. Now, the problem with this is that this describes a situation where we have just 2 distributions. We have our target and we have Q. What happens if we have t minus 1 distributions and we want to weight those particles instead? The answer is that there is an approach called multiple importance sampling, which says the following, that if you have samples from different distributions and you want to do the optimal importance sampling reweighting, the best approach is to actually assume that those samples come from the mixture distribution of all those previous distributions. So if we use this distribution as the proposal to calculate the weights, we get some formulas which look very messy, but what I want to show you here is that it's actually very cheap to implement. Have some weights for all those particles, all those p minus 1 times n particles, weights like that. You may notice here the weights the likelihood function, but we don't need to evaluate the likelihood again because we did so in the previous iterations and we have those values stored. And another thing to note here is that we also use those weights to compute the model evidence. And we get this new estimator of the model evidence, which is superior to the one that you can get from importance sampling, has much lower variance. So what I want you to remember from this slide is that we have a way to compute weights for all t-1 times n particles when we target the next PT, the next target. And we can also use those weights to get an estimate of the model evidence. Now, we said how to compute those weights. Our next question is how to choose the best n particles out of the t-1 n weighted particles. This is called resampling. And there are multiple approaches. Ideally, we want to choose each particle based on the value with a probability which is proportional to the value of the weight that was assigned to this particle. So if a particle has a very low weight value, we don't want to choose that one. If a particle has a high weight value, we do want to choose that one. So the simplest approach is to do what statisticians call multinomial regression. Let me describe how this sort of method actually works. Imagine that you have a wheel, like the one depicted here, and you place all your particles at the perimeter of this wheel. But because those particles, those t-1 times n particles are unequally weighted, we assign either arc lengths to those particles. So particles with high weight, high large arc. Those with small weight, take a small arc. And now we have all those t-1 times n particles in the perimeter, and we want to choose n new particles. So the natural thing to do is to sample just a rotation with wheel. So just choose a vector randomly from 0 to 2 pi. This vector constant, and we do this n times to get n new particles. The problem with this is that it's a very noisy technique. Even if you start with 100 particles that are equally weighted and you sample 100 new particles out of this, only about 60 of them will be unique. All the rest of them will be copies of the same particle. So this is a high variance resampling scheme. There are better ways to do so. We can still create this wheel, assign particles based on their weights in the perimeter of the wheel, and then we will sample a single vector and we place n-1 vectors equal handles relative to the first one. This way is more efficient, leads to much smaller variance, and this is the way that we chose for this method. Okay, so this tells us how to choose the best n particles out of this t-1 times n particles. As we already said, we need some way to move those particles around. Said that the reweighting and resampling steps do not actually generate particles, they just choose the best ones from the previous collection of particles. But we need a way to generate new particles. And the idea here is to use another technique called Markov chain Monte Carlo, or MCMC, which already mentioned this before, to move those particles around in parameter space, but preserving the correct target. So those particles, yes, are moving in parameter space, but not in ways that are violating our conditions from before. So those particles are still distributed according to PT, the target, the current target. There are many methods that can be applied here. There's random walk metropolis, like one of the simplest MCMC methods. There's slice sampling. There is Hamiltonian Monte Carlo, if you want to use gradients and so on. But as we will see very shortly, there's a much better method to use. So like I said, to go from the resampled particles to create some new particles, we use MCMC. In practice, this looks something like this. Those particles move around in parameter space. So they don't do as much effect. It's only for visualization reasons. And at some point, we just keep the final positions of those stored Markov chains. And these are the new particles. And once we do this, we're in the next iteration of the algorithm. We repeat again and again and again until we reach the posterior. So this is the main idea. We have these 3 steps. We have this collection of distributions. And to generate particles for the next distribution, the next and the next, we take into account not just the previous one, not just the previous distribution, but all the history. Okay, so far we've described pretty much everything except how to actually choose those distributions. Yes, we said that they have this functional form. Yes, we said that the weight parameter is interpolation is using this beta parameter over here, which goes from 0 to 1. But we haven't said anything about how to choose these values, beta 1, beta 2, beta t, and so on. to explain how to do this, first we need to talk about how to measure, how to count how many persistent particles we have. And by this, I don't mean count how many we actually have, because we know how many. We always have t minus 1 times n particles, but because those particles are weighted, not all particles are equal. So we need to take the weights into account. And one way, not a unique way, but one way to do this is to use the so-called effective sample size, which is defined like this. It's essentially the inverse of the sum of the square of the normalized weights. And what this means is, very roughly and very approximately, it means that n weighted particles correspond to ESS unweighted ones. So if you have 1,000 weighted particles with an ESS of just 100, just like having 100 independent particles from a distribution. Now, we can use this ESS notion to actually figure out what are these beta levels, so what are the beta values to bridge the gap between the prior and the posterior. And the idea here is that we keep an ESS constant or fixed throughout the run of the algorithm. So we say that we want at any point during the analysis, ESS to be fixed to a specific value, usually a multiple of the number of actual particles. Remember, the actual particles are n, so we just fix it to multiple of this. Can be either equal to n, or 2 times n, or half n, or so on. And this might sound a bit arbitrary, but there's good justification for this. And the idea is that ESS is equal to the so-called chi-squared divergence, which is, mathematicians in the room, please close your ears. This is sort of distance between two distributions. So if you have those two distributions, which are the two problems in our set of problems, this describes a sort of distance. It's not really distance, because if you took the opposite one, if you say you go from P to P1, gives you a different number than on the combination of this one. So it's not the distance exactly. That's why it's called divergence. But anyways, it sort of describes the distance between those distributions. So by fixing the ESS, by making the ESS be constant throughout the run, we're making sure that this interpolation between the prior and the posterior is a gradual one. It's a smooth one. It doesn't go very rapidly. It doesn't go too slowly. It always moves at the correct speed. And how do we determine this? We fix this parameter alpha here, which is the multiple of how many particles we actually have. So if alpha is equal to 1, ESS is actually equal to the number of particles that we generate in each iteration. If alpha is greater than 1, we have an ESS that's higher than the number of particles. This means that we have 100 particles that correspond to 200 particles because of the way they are weighted. And of course, alpha can also be less. Increasing alpha increases the computational cost of the method because it creates more beta levels between 0 and 1. And decreasing alpha makes this scale, this ladder, more coarse, more having fewer steps. So this is like the only hyperparameter that the user, the researcher, needs to take into account. By specifying alpha, you effectively specify how many effective particles you have, specifying the ESS. If you used nested sampling before for your analysis, this is essentially the number of particles that you use in nested sampling. Alpha times n is the same number. Okay, so this specifies how we split our very difficult problem into multiple ones. Now, let's look about this preconditioned notion. We already said that persistent sampling is a very general family of methods. But we also said that within this family, we're going to talk about a very specific method, PMC, preconditioned Monte Carlo. And we said that PMC has some very specific characteristics. One of them is this method called preconditioned Frank-Nicolson. Remember that I said that to go from here to here, you need some MCMC method. Well, preconditioned Frank-Nicolson is an MCMC method. Unlike random walk metropolis, which is like the simplest MCMC method there is, where you have a point parameter space, and in order to move that point, you just add some noise on top of it, and conditionally on some criterion, you move to the new point, and then you add noise again, and you move, add noise, move, and so on. Preconditioned Frank-Nicolson does something slightly differently. First, it takes the point, but instead of adding noise on top of it, it first sees the point, it moves the point toward the mode the peak of your distribution, and then as a rescaled version of that noise. By shifting first and then adding noise instead of just adding noise, this makes all the difference in the world. Unlike random metropolis that scales very poorly in high dimensions, and high here means anything above 5 parameters, preconditioned Crank-Nicholson can actually work in infinite dimensions. Can have an acceptance rate, so can still moving around, whereas maintaining a finite non-zero step size in infinite dimensions. You may say, okay, this looks very, very good. Preconditioned Crank-Nicholson sounds great. Why haven't I heard this before, right? Well, people using ground one metropolis pretty much always, and they don't use preconditioned Crank-Nicholson. The answer is that preconditioned Crank-Nicholson makes a very, very limiting and strong assumption. It assumes that your distribution really looks like this. It really looks like a Gaussian distribution. Some small variations from Gaussianity are okay, but the moment that your distribution significantly deviates from a Gaussian, doesn't work. Okay, so why then I'm using this for PMC? The reason is that we can lift this limitation, preconditioned Crank-Nicholson. And we can lift this by making the target Gaussian, by forcing the target to be Gaussian. I'm not making an assumption here. I'm not saying that we are only target cases where the target happens to be Gaussian. I'm saying we take a very complicated target that may looks really terrible, might have multiple modes, maybe skewed or whatever. And we force this target by transforming this target to be Gaussian so that PCN, preconditioned Crank-Nicholson, applies there. And this thing is called preconditioning in general, the art of transforming a distribution. And normalizing flow here is a fancy word from deep learning that means that this transformation that takes a target, which is non-Gaussian, and force this to be Gaussian, it's just parameterized by neural network. So if you take a transformation, which is bijective, so it's invertible, you can always go both ways here. You can always calculate the value of the density probably in more parameter spaces. Then if you parameterize this transformation using a neural network, then this is a normalizing flow. And as I mentioned already, the idea is we take a very difficult PT target, we manipulate this using a normalizing flow to look like Gaussian, approximately Gaussian, doesn't have to be perfect. Then we apply PCN in the latent space of that, where everything looks very symmetric, very nice, very isotropic. And then we transform all the samples. Can actually prove mathematically that this does not violate anything. You can always do that. Doesn't affect anything and so on. The trading? Yeah. Yes. Right. So, okay. Let me open a parenthesis here. Let me go to this picture here, right? Say you're at iteration number T, right? You don't know the distribution, but you have all -1 times n samples, which you just import and sample to look like anything. So you have a very good idea of what the distribution looks like. You retrain in every iteration. The number of iterations is not great. It's like for most astronomical small scale problems, like 20 to 30, 40, something like that. Training time is only important in the first iteration because you train from scratch, and then you just fine-tune the normalizing flow. So training in the first iteration takes 3-4 seconds in total, so it's quite significant. But from one to the next, it only takes about less than half a second. So if your likelihood function is the main computational bottleneck in your analysis, which is most often the case, then this is. Sorry? I guess you have any that having this converge to the right solution? Yeah. Yes, but no, but that's the great thing about this method, that you don't have to. As long as, not that I don't have a proof, it's also great. As long as the transformation improves things, makes things more Gaussian, you steer something correctly. It doesn't have, even if it's a terrible transformation, unless it breaks everything, which is never the case, it always improves things. It always makes sampling easier. It always makes sampling more It always makes a distribution more Gaussian. Maybe it fails to make something perfectly Gaussian, but that's okay. So going back to, so yeah, perhaps let me clarify this. Normalizing flows are often used as emulators. For example, we talked about simulation-based inference, where people use normalizing flows to do neural procedures. Yeah. Yes. Yeah. We found all distributions in 300 dimensions, no other sum particular. Yeah, that's it.
One last question about this. Is there no loss of information when you change, like from binary to primary distribution when you make it a Gaussian? Is there no loss of information?
No, because it's bijective, so it's invertible.
Yeah, but
It's 1-to-1, no loss at all.
it's curious how they're able to infer the function. Primary.
What do you mean by that?
I mean that I would have thought, I mean, without knowing about normalizing, that you change the distribution that like complicated multiple peaks into one with a single peak, that would be some loss of information.
Why this would there be is, I mean, forget about normalizing flow, right? Take a distribution in terms of parameter theta, okay? And then transform, and then take a transformation, which is the transformation from theta to theta squared. Okay, that's an invertible transformation. It's analytic. It's not a normalizing flow, or you can think of this as a very, very simple normalizing flow, right? But it's invertible. You can always go from one distribution to the other. One of them is bimodal, the other one is not.
Mm-hmm.
Does that make sense?
Yeah.
Okay, if there are questions about this, we can stay on this a little more, but otherwise I can continue. The important thing here to remember is that the normalizing flow is not used as an emulator. It doesn't replace the target or anything like that. We use just a transformation to make the space where the target lives flat, or as flat as possible. Now, let me show you some examples. First, we have these 4 different benchmarks. Those are all toy examples. So the Rosen distribution looks like a banana, very aggregated in 10 dimensions. Have a bimodal distribution in 30 dimensions in this case. This is 2 Gaussian peaks that are unequal in size and well separated. Gamma distribution in 30 dimensions. These are 4 well separated peaks that are not Gaussian. And we have a funnel distribution, which is a distribution that looks like a funnel, something like a tornado and distribution. This is very common if you have hierarchical Bayesian models, and it's a very, very difficult target. And what I show you here is the number of calls, how many times you need to evaluate your likelihood function or your model to get to the answer, to get the procedure. And we compared here 2 different methods. We compared PEC, our method, nested sampling. And for both methods, for either method, we use 2 different techniques. For PMC, we use, of course, PCN. So I justified this is very good. And we also use random walk metropolis, just to show how PCN improves upon random walk metropolis. For nested sampling, we use random walk metropolis and slice sampling. You may ask, why not PCN for slice sampling? The answer is because it's impossible to implement in nested sampling. And here we show you the total computational cost. So lower is better, higher is worse. You see here that in general, PMC is always lower than nested sampling, irrespective of what method we're using, what instance method we're using. And we also see that PCN is always lower than random walk metropolis. Next, we move on to a benchmark about the estimate of the model evidence. Here, we estimate that parameter Z, that value is Z. Here, so you data low Z is a true value. So here, we want to get to 0. It's here that in low-dimensional problems like this nested sampling can actually get pretty close. In higher-dimensional problems, nested sampling has trying to get into the correct answer, provides biased results. Whereas PHC always gets to the answer, and the variance is also very small. This is also, again, for the same 4 different problems. Now, so you have the method scales with a number of parameters, the number of dimensions. Here, example where we go from 0 to from 1 to 28 dimensions. And here show you the number of calls, or the computational cost per particle. In the limit where the number of particles is very high, this should converge. And again, we do the same for different flavors of those methods. You can see here that PMC with PCN orders of magnitude more efficient than nested sampling. It's actually more efficient to run PMC with PCN in 128 dimensions and we run nested sampling in 20. And this is all because of PCN, of the way that it scales per dimensions. Yes, but it's a log scale on the y-axis. So if it was in a linear axis, the slopes of the lines would be different. Next, we look into how the evidence estimate scales the number of dimensions. Here there is a Gaussian distribution, so very single target. See here that we go current dimensions. PMC maintains its accuracy, whereas nested sampling actually struggles. The results here, irrespective of the MCMC method that we're using, this only affects the computational cost, nothing more. Finally, let me show you a cosmological example. This is only 6 of the 20-something parameters in the Archimedes survey year 1 analysis. And here we tested 3 different samplers. The target was to collect enough samples to have an effective sample size of 10,000, irrespective of the sampling method that we use. And we use random walk metropolis. We use state-of-the-art no-return sampler, which is like method of choice if your problem is differentiable. And of course, we use PMC. Number of CPUs and everything else was the same. And you can see here the results. Random walk metropolis took more than a day to finish sampling. NUTS took a few hours. PMC only 20 minutes. If there is time, I will mention a few connections with some other methods. Okay, so this is the general picture of persistent sampling. Collections of problems that we solve all those distributions. The idea was that at every distribution, we rely on all past iterations, on all past distributions. So it looks like this. At any point, we have all those particles at our disposal. Now, persistent sampling is, as I mentioned, a very general family of methods. One of the members of the family, apart from PMC, is sequential Monte Carlo, which is a very popular approach in some other fields, not necessarily. Then the sequential Monte Carlo is a version of persistent sampling, only including these particles, discarding all the previous ones. Turns out also that nested sampling is also a case of special case of persistent sampling, but you start it like this. So you always add one more particles, and your ensemble of particles is distributed across time, not across space. There are a few more differences or choices that need to be made to make persistent sampling look like nested sampling. Instead of using a temperature annealing schedule, we use an energy annealing schedule, so we keep constant energy, constant likelihood. This case, but for those not familiar with nested sampling, it's a very elegant technique. The idea is that you take the integral of the evidence that I showed you, you transform this to a one-dimensional integral, and then instead of solving this as a Riemann integral, you solve this as a Lebesgue integral. The advantage of using persistent sampling as nested sampling, instead of just using nested sampling, is that it is a pure Monte Carlo method. It has a well-defined termination criterion that nested sampling doesn't. Also, nested sampling is not pure Monte Carlo, it relies on trapezoid rules and stuff like that. And it is unbiased, unlike nested sampling. And also, it leaves a significant limitation of nested sampling. Every time you add a new particle in nested sampling, you need to make sure that this particle is independent. Otherwise, you introduce bias. If it's correlated but not independent, doesn't work. This method works even with correlated particles, you still get unbiased results. In that sense, nested sampling is a numerical approximation to persistent sampling with these choices of annealing. Finally, a few words about the software implementation of this. A few weeks ago, we introduced a new version of POCMC. This is a Python package you can find online on this website, along with detailed documentation and examples of how to run this. This is a very short example of how the code looks like. Find your prior distribution, find the likelihood function, repeat both of them to the sampler, you type run, and then you get the results. Finally, I won't leave you with conclusions or a summary or anything like that. I will try to leave you with a take-home message. I think that as the amount of data that we collect and the complexity of the model that we have increases, we'll need samplers that will scale better to higher dimensions. And not only scale better for higher dimensions, but also do so for challenging distributions that are multimodal, distributions that are very nonlinear. And I think that POCMC makes a strong case, and PMC as the method, for one such sampler. This meta gives POCMC sampling itself. And you can find the code here and the documentation there. Thank you very much.
Thank you very much. Very interesting.
No. High dimensional problems, like if you go to, I know, this will never scale to 1000 dimensions because it's limited by the ability of the normalizing flow to precondition the target. If we ever get normalizing flows that work in 1000 dimensions, this would be great. Another limitation, so in high dimensions, if your target is unimodal, doesn't have multimodality, use nuts. Of course, if it's differentiable. Another problem is that this method, by design, starts from the prior distribution and goes to the posterior distribution. So if your prior is very, very, very broad compared to your posterior distribution, so if you're very, I don't know, if you want to use huge prior range, very high dimensions, then this will delay the convergence because you need to actually integrate all those distributions together.
And this by distribution. You need this focus between
right.
By doing your
there is a single case where this does not work. As John Skilling, like the father of nested sampling, would say, SMC methods and methods based on temperature annealing do not work if you have a phase transition. So if your likelihood function, yeah. Fortunately, we never have this in astronomy. If you're doing material science and you want to create various diagrams that those people use, then this annealing scheme, the temperature one, is not ideal. But this does not restrict you from using the energy annealing scheme, which essentially is nested sampling with some modifications. So in terms of that, if you don't have phase transitions from prior to posterior, then you can always guarantee that it is smooth. Yeah. Thank you. What do you mean low dimensional? How many parameters? 3, 4, probably any method you use would be fine. I mean, in 3 dimensions, you can even do a grid search and compute your posterior that way. So I don't know, it depends on the problem. Relating this to the previous question, this method is good if your model is very expensive. So if your likelihood function, irrespective of the number of dimensions you're using, is very expensive, takes too long to compute it, more than a few milliseconds, then this is great. If your likelihood function is very fast, then you're probably better off using some other method, some probably simpler method, I would say. I think was the question first. So Right. But you don't need, okay, there are two ways to, there are many ways. There are two common ways to train normalizing flow. One of them is you have samples from a distribution and you want to do density estimation. You want to learn what's the density, the probability distribution of those samples. For that, you don't need to know the gradient of that distribution. Just the neural network uses some gradients internally, but that's not the gradient of your target. You only use the sample from the target. The other way is you don't have samples from your target. You have the distribution, so you can evaluate it at any point you like, and you want to train the normalizing flow to learn that. This is called variational inference. In that case, you need to know the gradients of that target. But in this case, you do not. It all depends on what loss function you're using.
I think we should stop. Sorry about that. It's basically my I need to give Andreas his last week for life. So let's thank Minas again. Minas will be with us again tomorrow. We're going to get dinner organized tonight and tomorrow also. So those I know that some of you cannot make it will arrange this. Is someone going for lunch at 4? Can you go with us and discuss a bit and let me back to here so that is simple? Okay. No, we like the comment. Okay. Okay. Thank you very much. So we'll